This research paper, titled, A Case Study Exploring the Current Landscape of Synthetic Medical Record Generation with Commercial LLMs, is authored by Yihan Lin, Zhirong Yu, and Simon A. Lee from the University of California, Los Angeles. It was published in the Journal of Machine Learning Research and presented at the Conference on Health, Inference, and Learning in 2025. Synthetic electronic health records, or EHRs, are artificially created versions of real medical data that help protect patient privacy while still being useful for research and AI development in healthcare. The paper highlights how these synthetic records provide key benefits, such as allowing precise control over the data's structure, improving fairness by better representing diverse patient populations, and enabling safe data sharing without risking real individuals' privacy. Large language models, or LLMs, which are advanced AI systems trained on vast amounts of text, have become popular for generating this synthetic data across various fields, including healthcare. However, the authors point out a major challenge: ensuring that these synthetic health records can reliably work across different hospitals, where data structures and patient populations vary widely. This has been a persistent issue in healthcare AI. In this study, the researchers evaluate how well commercial LLMs perform in generating synthetic EHRs. They investigate several aspects of the generation process, including how the models handle different sample sizes, the complexity or dimensionality of the data, and measures of fidelity, meaning how accurately the synthetic data mimics real data, and privacy. Their main finding is that while LLMs are quite effective at creating synthetic health records for smaller sets of features, they struggle when the data becomes more complex. Specifically, these models have difficulty maintaining realistic distributions and correlations between variables as the number of features increases. This limitation means that synthetic data generated by LLMs may not generalize well to diverse hospital settings, potentially undermining its usefulness in real-world applications. To conduct their research, the team used data from the EICU database, which is a large, multi-center collection of de-identified health data from over 200,000 ICU admissions in the United States between 2014 and 2015. They accessed this through enterprise accounts for various commercial LLMs, noting that the specific model checkpoints could affect reproducibility. Importantly, their work did not require institutional review board approval since they used de-identified data. The introduction of the paper explains how LLMs have advanced AI research by excelling in natural language understanding and generation. In healthcare, they're particularly valuable for creating synthetic EHRs that are structured, consistent, and privacy-focused. For instance, LLMs can help generate data that includes underrepresented groups, addressing limitations in traditional datasets like Mimic or the UK Biobank. Despite these advantages, challenges remain in ensuring that synthetic data is generalizable across different patient populations and data formats. The authors reference ongoing efforts in data harmonization, such as frameworks like MEDS and schema matching techniques, but argue that these haven't fully solved the problems yet. This makes synthetic data generation a promising but imperfect approach for creating adaptable datasets. In their methodology, the researchers explored various generation strategies with LLMs. They focused on factors like the size of the data samples, the dimensionality, which refers to the number of variables or features in the dataset, and how well the synthetic data preserves realistic patterns. To assess generalizability, they performed multi-site validation using real data from the EICU database. For evaluation, they employed a benchmarking framework based on XGBoost, a machine learning algorithm known for its robustness. This allowed them to measure how well the synthetic datasets could be used for predictive modeling, effectively testing their fidelity and utility. This approach fills a gap in previous studies by providing a more comprehensive assessment of LLM-generated synthetic data in healthcare contexts. The paper emphasizes the importance of this problem, noting that fair and representative datasets are essential for building equitable AI systems in healthcare. Current issues like limited data access, lack of diversity, and inherent biases in real datasets can lead to unreliable and unfair AI models. Synthetic data offers a solution by enhancing diversity and protecting privacy, but the authors stress the need for rigorous studies to evaluate its robustness. Throughout the paper, they discuss how LLMs can generate datasets that are more inclusive, for example, by simulating health records for marginalized groups that are often underrepresented in real-world data sources. This could help mitigate biases and improve the overall reliability of healthcare AI applications. In terms of specific findings, the researchers found that for low-dimensional data, meaning datasets with fewer features, LLMs could produce synthetic records that closely matched real distributions and correlations. However, as dimensionality increased, the models failed to capture the complex interrelationships between variables, leading to synthetic data that didn't reflect real-world scenarios accurately. This has implications for privacy as well. While synthetic data is designed to protect individual identities, the paper notes that if the generated data doesn't preserve realistic patterns, it might not be as useful for training AI models that need to handle varied hospital environments. The authors suggest that future work should focus on improving LLM's ability to handle high-dimensional data and ensure better generalizability. Overall, this case study provides a critical examination of the current capabilities of commercial LLMs in synthetic medical record generation. It underscores the potential of this technology while highlighting key areas for improvement, such as enhancing model performance with complex datasets and ensuring that synthetic data can be harmonized across different healthcare settings. By doing so, it contributes to the broader goal of advancing ethical and effective AI in healthcare.